Hello everyone, my name is Ozan Karatas and I'm coming from Turkey, from Ankara University. Today I will talk about the pasteurization, especially innovative new methods such as microwave heating. For this study, we developed a mathematical model and we validated this model with two different experimental studies. As everyone knows so well, beer is the most widely consumed and the oldest alcoholic beverage in the world and has many stages in beer production. Today, we will focus on final stage pasteurization. Pasteurization Pasteurization is applied to reduce the microorganism load in beer and to increase the shelf life. The most frequently used method is the conventional heat treatment method. And the conventional pasteurization might be applied with two approaches. One is to pasteurize the bottle or chemical product and record it tunnel pasteurization. The other option is to pasteurize the product in a continuous system and then package the processed product. And it's a glass pasteurization. The target microorganism in beer pasteurization process is Saccharomyces cerevisiae, and the reference temperature of this microorganism is defined as 60 degrees Celsius, and Z value is 6.94 degrees Celsius in the literature. These, uh, these values were used to evaluate the effectiveness of the pasteurization process applied. Uh, in an effective pasteurization process, it's necessary to reach between 15 and 30 pasteurization units and microwave process, which is considered as an innovative method instead of conventional methods, was used in this study for pasteurization of beer. As known, there are two allowed frequency values for microwave heating. One of them is 900 megahertz, and its wavelength and penetration depth is greater than the frequency of 2400 megahertz. The 900 megahertz frequency is mostly preferred in industrial application. In domestic ovens, the shorter wavelength, 2400 megahertz frequency is used, and for our studies, we use a domestic oven, so we prefer mathematical models with using 2450 megahertz frequency. The faster thermal processes occur with using the microwave system. In addition, the heat generated in the product is formed hermetically, unlike the conventional method. However, there are some points to be considered here. Irregular electromagnetic fields occurring in microwave cavities, and it causes inhomogeneous temperature distribution in the product. For this reason, the electromagnetic fields from inside should be calculated very well, and optimum system parameters should be calculated for a homogeneous temperature distribution within the product. Uh, we separate our studies to three stages. One of them is experimental studies. Second one is the modern development and validation with experimental studies. And finally, continuous system design for beer pasteurization. A domestic microwave oven was used in our experimental studies. In order to use liquid product in this oven, there is a Teflon tube inside our cavity, and that is completely transferred to the microwave. We processed liquid samples by feeding them Teflon tubes. Our scale microwave oven works with a maximum power of 700 watts. Uh, in experimental studies, firstly, our experiments were carried out in distilled water for model validation. For these experiments, temperature measurement was taken using fiber optics and 5.6 centimeters below the top surface of Teflon tube. In the presentation, the temperature measurement location taken from the distilled water is shown with a red point. After distilled water experiments, non-pasteurized beer samples were used for this study. The temperature measurement was taken from the non-pasteurized beer samples from the place indicated by the blue point. Uh, Initial temperatures were measured as 24 and 8 centigrade Celsius for distilled water and beer respectively. When using high power or maximum power settings, unwanted foaming occurred in beer. So all experimental studies have been done at mid-power settings. The large scale microwave oven works with an on-off power cycles. These power cycles you have seen was obtained throughout the experimental studies with distilled water experiments, and it was used in the mathematical models. Thermal and physical properties of distilled waters taken from the library of Computational program, and the reactive properties of distilled water were measured by the certified research group in previous studies, and these were used in the mathematical models. Thermal and physical properties of beer were taken from the studies in the literature. The beer used in this study are non-pasteurized beers belonging to the Ankara company. The dietetic properties of these non-pasteurized beers were measured at different temperatures using network analysis method, and these obtained data were used in the prepared mathematical model. And second stage is a model development and model validation. The geometry of the large-scale microwave oven used in experimental studies was drawn in real dimensions with using Computational program. And also, our large-scale microwave oven has a coaxial magneton, and this magneton is defined as you can see the presentation. Also, all interior walls of the microwave system are defined as a perfect AD conductor. For liquid samples in Teflon tubes are defined as a fluid. In addition, the heat product boundary condition was defined so the convection heat transfer realized with the emission air on all Teflon tube walls. These equations were used in our mathematical models. And after modern validation, the large scale oven has been modified for a continuous microwave pasteurization system, and non-pasteurized beer samples with an initial temperature of 4 degrees Celsius, and this non-pasteurized beer flow through this modified microwave system. Since the modified microwave system is a large scale, every flow rate is preferred. Thus, laminar flow was formed inside. However, this flow rate should be higher in industrial system. Our mesh profiles, as you can see in the presentation, uh, when the experimental studies using distilled water and the mathematical models of these studies are examined, uh, it seems that the results obtained are very close to each other, and root mean square error was calculated to 2.66 degrees Celsius. The temperature and electromagnetic distribution within the product, as you can see in the presentation, depending on the microwave system geometry, the electromagnetic field formed in the system is concentrated in the upper part of the system. For this reason, the upper part of the distilled water in the Teflon tube are warmed more. Also, Also, you can see the profile in XY section taken from the product and temperature distribution within the product by the format. Compared with experiments with non-pasteurized beer and the mathematical models results of those experiments, it's clearly seen that the results are very close to each other, and the root mean square error was calculated 2.52 degrees Celsius, and the temperature and aromatic distribution from inside the product are similar to distribution obtained in distilled water. The temperature values in region where temperature measurement is taken using fiber optics are around 66 degrees Celsius. You can see the uh, in this page, you can see the profile and temperature distribution in the product. Uh, and finally, when we examine, when we investigate the results of the continuous microwave system modified after model validation, the target temperature for the pasteurization process is 60 degrees Celsius was reached by using 4,000 watts power. During the microwave process applied at different power, the temperature profiles found within the product are shown in the presentation. It seems that 3,000 watt power application is not sufficient for pasteurization process. Also, it is seen that using the 5,000 watt power is above the target 60 degrees Celsius. After using 5,000 watt power, the product leaving out of the microwave system reach 72 degrees Celsius, and this is the temperature profile within the product when we use 4,000 watt power. With using the 4,000 watt energy, the microwave process ends after 85 seconds. The beer samples leaving the microwave system reach 0.25 pasteurization unit, and however, this pasteurization value is not enough for pasteurization. For this reason, it must be kept in a holding pipe at constant 60 degrees Celsius for a certain period of time. The holding pipe length required 4.3 meters, and the required time is 865 seconds. After this process, the beer sample completed complete the pasteurization process and reach a 15 pasteurization value. And another target temperature for flash pasteurization is 72 degrees Celsius. Pasteurization process is completed by keeping this temperature value for a short time. In this case, the energy required for microwave system is 5,000 watts. The temperature profile resulting from the use of 5,000 watt power, as you can see in the presentation. The beer samples reach 72 degrees Celsius at the end of the microwave process after uh, 85 seconds with using 5,000 watt energy. As a result of this process, the pasteurization process is completed in the beer samples leaving from the microwave system, and beer samples reach 17 pasteurization unit. Since the required pasteurization unit is reached after the microwave process, no holding pipe stamp is needed. Uh, with these results, it has been shown that beer pasteurization can be achieved by microwave process. Pasteurization beer samples should be packaged under the aseptic condition, and the carbon dioxide removed from the product during the microwave process should be added back to the beer samples. Thank you for your attention. Also, this study was supported from Ankara University and Anadolu Efes Company, so I thank them for their contribution too. If you have any questions, I'm happy to answer from Turkey. Thank you very much.